Good morning, students. In today's class, I will explain some concept that you need to know in order to understand the process of CPU scheduling. What do you mean by CPU scheduling? In a multi-programming system, several programs are there in the main memory or ready queue, and only one CPU is there. The same CPU has to service all the process which are waiting for it. Then, in which order the processes which are waiting for the CPU are serviced? Which process will be executed first? Which process will be executed next? These things are decided by an algorithm called CPU scheduling algorithm or CPU scheduling policy. The technique of allocating the CPU to one of the process in the ready queue based on some order, we call it as CPU scheduling. In last class, we learned about some basic information regarding process concept or process scheduling. We also learned the different states of a process. A process, when it is first time submitted, it is said to be in a new state. From the new state, the process first has to enter the ready state. And once the CPU is free, then if the CPU start executing a particular process, at that time, the process is said to be in a running state. And if the process needs some input output operation to be done, in that case, the process moves from running state to waiting state. After completion of its IO operation, once again the process moves to the ready state. And whenever the CPU is allocated, it moves from the ready state to running state. After the process execution is completed, the process moves to the last state called terminating state. In any CPU scheduling, the complete description about a process is available in a special register called process control block. A process control block contains the complete description or complete information about every process. It stores the information like process number, process priority, then some CPU scheduling policy details, memory management information, and what are all the available registers, CPU register, general purpose register, stack register, all this information is available in the process control block. In today's class, we will be learning about the different categories of CPU scheduling policies and also what are the criteria based on which we select a suitable CPU scheduling policy for our application. At the end of today's class, you will be in a position to understand the differences between the two categories of CPU scheduling policies, namely preemptive CPU scheduling and non-preemptive CPU scheduling policies. In addition to that one, you will be able to understand the some of the CPU scheduling criteria. The criteria decide the goodness of a particular CPU scheduling algorithm. So on what basis we have to select a suitable CPU scheduling policy for our application is decided based on these criteria. We know that CPU scheduling takes place in one of the following circumstances. That means CPU moves from one process to another process if any of these four circumstances occur. The first case or first situation is when a process switches from running state to a waiting state. When a process moves from running state to waiting state, when the process needs some IO operation to be completed, mean in that case, from the running state, the currently running process moves to the waiting state. At that time, the CPU start executing some other process in the ready queue. So during this situation, the CPU moves from one process to another process or CPU scheduling takes place. The second situation is when a process switches from running state to ready state. This happens whenever or during interruption operation. To understand what you mean by interrupt, you can consider a simple example. Let us say your CPU is executing a process labeled X. Whenever the CPU is executing any process, the particular process is said to be in a running state. Now, the process X is in a running state. At that time, another new process called Y arrives. The priority of Y is higher than the priority of X. In that case, what happens is the currently running process X is moved from running state to the ready state, and the process Y started executing by the CPU, and the process Y is moved from ready state to running state. So in that situation also, the CPU moves from the process X to the process Y. So this is the second situation where CPU scheduling takes place. And the third case or third situation is when a process switches from waiting state to ready state. So this happens after the particular process which previously requested for an IO operation has completed its IO request. In that case, after completing the IO request, it moves from waiting state to ready state. At that time, suppose the CPU is free means, then the CPU moves to execute this particular process. So this is the third situation where your CPU scheduling takes place. And the last one is when a process terminate after the execution of the current process is over, automatically the CPU picks up the next process in the ready state. So during this situation also, the CPU moves from one process to another process. So these are the four circumstances where the CPU switches from one process to another process. Based on which of these circumstances occur, CPU scheduling algorithms are broadly classified into two types. One is non-preemptive algorithm, other one is preemptive algorithm. The difference between these two is whenever CPU scheduling takes place in the first situation or the last situation. The CPU scheduling takes place when a process switches from running state to waiting state or when the process execution is terminated. If CPU scheduling takes place in these two situations, we say that the CPU scheduling algorithm is non-preemptive in nature. Some of the examples of non-primitive or non-preemptive CPU scheduling policies are first come, first serve, and shortest job first. Anyway, I'm going to explain in detail with their merits, demerits, features, everything in my next class. And if the CPU scheduling takes place during the second or the third situation, that is, whenever a process switches from running state to ready state, this is during interruption, or when a process switches from waiting state to ready state, this happens after the process completes its IO operation. If the CPU scheduling takes place during these two circumstances, we say that the algorithm is preemptive in nature. Example is one example of preemptive algorithm is round robin CPU scheduling policies. To understand the difference between non-preemptive and preemptive, we consider one simple example. So in a simple term, a preemptive algorithm is like this. Under non-preemptive scheduling policy, once a particular process is allocated the CPU, once a particular process gets the CPU main, then that process will give the CPU to the next process only in two situations. One, it has to complete its execution. In that case, automatically it goes to terminating state and the CPU switches to the next process. Or only if the particular process has any IO operation, then only the CPU goes to the next process. Otherwise, what happens is once the process is allocated CPU, it keeps the CPU with it until it is completely executed. In no way we can forcibly take the CPU out of that particular process and give it to the next process in the ready queue. Whereas in case of preemptive, what happens is even though no IO request is there, and even if the process not completed its execution also, after some time duration is over, automatically the CPU is scheduled to execute the next process which is waiting in the ready queue. It's simple like this. In your house, suppose there is only one laptop and yourself and your brother, sister, three of them are depending on the laptop mean. There are two situations. Once you get your laptop to use mean, you can give the laptop to either to your brother or sister in two situations. One is after all your online classes are over, you can give the CPU to your brother or sister. Or in between, suppose if you want to take some rest, at that time also, you can give the laptop to your brother or sister. If you give the laptop in these two situations, we say that it is non-preemptive in nature. The second situation is after every 1 hour, after first hour, you use the laptop. After first hour, you give the laptop to your brother. Let him use the laptop for 1 hour. Then pass the laptop to your sister. Then after each of you get 1 hour laptop usage means, then you can utilize the laptop for the second term. So such situation we call it a preemptive CPU scheduling policy. In this case, your utilization of getting laptop is getting CPU. Let us see the major differences between preemptive and non-preemptive algorithms. In the case of preemptive algorithm, a processor can be preempted to execute another process in the middle of the current execution process. A particular process gets a CPU, it keeps on executing that process. in between another process arrives, the priority of which is higher than the currently running process. Means in middle only, the CPU leaves this process in the middle and goes to the next process. And in case of preemptive algorithm, the utilization of the CPU is efficient because the CPU will be busy always. First, it will execute the first process for some time, go to the next process, execute that process also for some time, go to the next process in the ready queue, execute every process for some duration. So in that case, what happens is CPU is moving from one process to another process. To keep on executing either one process as the other process means the utilization of the CPU is better in case of preemptive. Next, the waiting time and the response time of preemptive CPU scheduling algorithm is less. The reason is once a particular process gets a, first for example, there are three processes P1, P2, P3. First, CPU is allocated to P1. Then P1 cannot hold the CPU indefinitely till its execution is completed. After some duration, automatically, after some, suppose after one time quantum, say it is 20 millisecond. After 20 millisecond, automatically CPU is allocated to P2. In that case, P2 has to wait only for 20 millisecond. Then after executing the process 2 also for 20 millisecond, then it goes to process 3. In that case, what happens? For process 1, waiting time is 0. For process 2, the waiting time is 20 millisecond. For process 3, the waiting time is 40 millisecond. For process 4, it is 60 millisecond, etc. So everybody has to wait for some duration, and the waiting time will not be too much for any particular process. Not only the waiting time, even the response time is also less in case of preemptive scheduling policy. Anyway, I'm going to explain the term response time, waiting time, etc. in subsequent slide. Preemptive algorithm suffers from one major drawback, the overhead. Suppose your CPU is executing the process X. All of a sudden, a new process Y arrives. The priority of Y is higher than the priority of X. In that case, some time is wasted because first the process X, which is currently in running state, should be moved to another state called ready state. Then in that case, it has to refer the process control block of process P1, make some changes there, then brings up then another process called Y because the priority of which is higher. Then again, in that case, again, it has to refer the process control block of P2, make some changes there. After the execution of process P2, once again, it has to refer a process control block of process 1, make again some changes, bring back the process X and start executing. So during this movement from one process to another process, some time is wasted. The time we call it a overhead time. So the overhead time is little more in case of preemptive algorithm. In the case of non-preemptive algorithm, once the processor starts its execution, it will move to the next process in only two cases. One, either by completely executing the currently running process, or the currently running process has any IO operation, then only the CPU moves to the next process. But in case of CPU, in case of non-preemptive, what happens is the utilization of the CPU is not proper. The reason is one process, suppose the particular process P1 is too big, then it will keep the CPU for longer duration. So utilization of CPU is more for P1. Suppose the second process P2 need only some 5 milliseconds of CPU time. In that case, it can keep the CPU only for 5 milliseconds. So the duration in which CPU is allocated to any particular process, that depends on the size of the process. So all the process cannot have the same CPU utilization. Third one is the waiting time as well as the response time of non-preemptive policies are higher than the corresponding preemptive policies. And non-preemptive algorithm, there is no such overhead because the CPU scheduling takes place in case of non-preemptive only two cases. One is after completely executing the currently running process, automatically the CPU moves to the next process, which is there in the ready queue. Or only if the particular currently running process needs some IO operation, in that case, CPU will not sit till the IO operation is completed. Automatically, it goes to the next process in the ready queue. In other cases, it will not move at all from one process to another process. Means that overhead going to the transferring one process currently running process to a ready state, bringing the new process, all such transition is not there in case of non-preemptive policies. In case of preemptive scheduling policy, we can prioritize the process. Whenever what happens is some high priority job has to be executed, means automatically the CPU stop executing the currently running process by moving or changing its status from running state to ready state, automatically it will execute the high priority job. So the prioritization of the job is left to the user discretion means. So it will have more flexible. So in the case of preemptive, since the process, all the process can be prioritized. The highest priority is a process that is currently utilized the CPU. And it is compared to non-primitive, it is much more flexible. Because in case of preventive algorithm, depending on the priority of the job, the CPU scheduling will move from high priority, low priority jobs to high priority job automatically. Example of preemptive policies, round robin. In case of preemptive policy, the CPU is allocated to the particular process for only specific period of time. After the specific time period is over, automatically by forcibly CPU is removed from that process and given to the next process in the ready queue. In case of non-preemptive, when any process enters the state of running, it will, in that case, what happens is, unless the process completes its execution or unless the process needs some IO operation, forcibly, we cannot remove the CPU from that particular process and given to the next one. That is not possible. And hence, non-primitive scheduling policies are very rigid in nature. You don't have any flexibility in executing any of the high priority job first. Examples of non-primitive scheduling policies are first come, first serve, shortest job first, priority scheduling, etc. So already I told, in the only two situations in case of non-primitive, CPU scheduling takes place only when the process terminates or only when the process requests an IO operation. Let us see some advantages of preemptive algorithm versus non-preemptive algorithm. So here, the left-hand side of the paper, left-hand side of the table gives the advantages of preemptive algorithm, and right-hand side of the table gives the advantages of non-preemptive policies. In case of preemptive, CPU utilization is same for all processes, because once a particular process gets a CPU mean, it cannot hold the CPU for very long duration. After a time slice is over, automatically the CPU goes to the next process, which is waiting for it in the ready queue. Execute that process also for some time quantum duration, moves to the next process. So here what happens is, every process can keep the CPU only busy only for specific period of time. The CPU utilization is same for all process, and the response time is more uniform, because every process, the waiting time is also there, and for every process response time is also there. One process need not wait for very long duration, so that is not there in case of preemptive policies, and it is more robust. So we can tune a preemptive algorithm according to the priority of the job on our own. Some of the advantages of non-preemptive scheduling policies are, it is less overhead, because even if high priority jobs comes also, it cannot be given the CPU immediately. So no switchover is there, and it is easy to implement. And when compared to preemptive algorithm, non-preemptive algorithm utilizes less computational resources. At the same time, both the algorithm suffers from certain drawbacks also. In the case of preemptive algorithm, it takes higher time by the scheduler to suspend the running task, because first it has to suspend the running task whenever a high priority jobs come, switches to the high priority job, and then after execution, the high priority job is over, once again switches back to the previously executing job. So that switchover time is little bit more in case of preemptive policies. And another major problem with the case of preemptive algorithm is, assume that the CPU is currently running a process called X. All of a sudden, a new process Y arrives, the priority of which is higher than the priority of X. In that case, X should be moved from running state to ready state. Then the CPU start executing Y. By the time CPU completes executing the process Y, another process Z arrives, the priority of that one is again higher than X, means X will not get the CPU again. So the CPU is allocated to Y now, sorry, Z now. After executing X and Y and Z, another process P arrives. The priority of P is also higher than X, means X will never get the CPU. So here what happens is, whenever high priority jobs or high priority process are keep on coming, mean they prevent the low priority process from getting the CPU for very long duration. Next, a non-primitive algorithm, some of the drawbacks are, it is not suitable for time sharing system. Already in my previous class, or probably before that one, I've explained the purpose or meaning of time sharing system. In a time sharing system, nobody can hold the CPU for very long duration. No process can hold the CPU for very long duration. a time limit is set called time step. After for every process, the CPU in one rotation given maximum of one time quantum. After the time quantum period is over, automatically CPU switches to the next process. But in the case of non-primitive, what happens is once a particular process is allocated the CPU, it will release the CPU in only two situations. One, either by completing its execution or only by whenever it has some IO operation. So hence, a non-primitive algorithm is not suitable for time sharing system. And the waiting time is not uniform in case of non-primitive algorithm. Suppose we have three process P1, P2, P3. P1 require 100 millisecond, P2 require 10 millisecond, and P3 require 5 millisecond. In that case, what happens is P1 will get the CPU first mean its waiting time is 0. Whereas P2 will get the CPU after 100 millisecond. And P3 will get the CPU after 100 plus 110 millisecond because the first process has 100 millisecond requirement. Second process need 10 millisecond and the last process require only 5 millisecond. Just for getting the CPU for just for 5 millisecond, it has to wait for 110 millisecond. The one process no waiting time. For one process the waiting time is too much. Hence, the average waiting time is not uniform in case of non-preemptive policies. Next, there are so many algorithms: first come first, shortest Java, round robin, etc. Then, which is a better algorithm for my application? So that is decided based on some 5 criteria. Some of the criteria related to CPU scheduling policies are: the first one is CPU utilization. What do you mean by CPU utilization? How much you are keeping the CPU busy, how best you are keeping the CPU busy, that indicate your CPU utilization. Suppose there is a process called P1. For that particular process, 20 milliseconds of CPU is allocated in one rotation. Suppose out of 20 millisecond time it allocated to it, suppose that process utilize the CPU for only 10 millisecond, remaining 10 millisecond, it is busy with doing IO operation or it is waiting for IO request, IO operation mean, then out of the allocated 20 millisecond, it is keeping the busy only for 10 millisecond mean, its utilization is only 50%. Let us take another example. Say another process P2 is there. For that one also, CPU allocated in one rotation for 20 milliseconds. Suppose that process keep the CPU busy for 15 milliseconds. That means it is it is under execution by the CPU for 15 milliseconds. Only for the remaining 5 milliseconds, it is doing IO operation means its utilization is 75% because out of 20 seconds, it is keeping the CPU busy for 15 milliseconds. So its utilization is 75%. So higher the CPU utilization, better is the algorithm. So always try to keep the CPU as busy as possible. Then we say that your utilization is good. Suppose in your ready queue, all the jobs are 100% CPU bound job. That means none of the job has any IO operation means. In that case, CPU utilization is 100%. Suppose all the processes in the ready queue are IO bound job means they don't require CPU. In that case, your CPU utilization is only 0%. Hence, the CPU utilization is expressed in percentage by varying from 0% to 100%. So this is the first criteria which decide the goodness of CPU scheduling algorithm. The second one is throughput. Throughput is the number of process that can be completed per unit time. That means in the allocated time given to you, how much process you can completely execute. So to understand that one, let us consider 3 different processes. Process 1 is 15 millisecond, process 2 is 6 millisecond, and process 3 is 8 millisecond. First one is 15 millisecond, process 2 is 6 millisecond, and process 3 8 millisecond. Suppose in one rotation, only 20 millisecond was given to user 1. She has written already 3 programs, P1, P2, P3, requiring 15, 6, and 8 millisecond. So if you execute in the order P1 first, then P2, and then P3, then in 20 milliseconds, how many process you can completely execute? If you execute in the order P1, P2 means P1 itself take 15 milliseconds, you can completely execute only P1. Because in order to execute P2, we need another, how much time? Another 10 seconds. So first one is 15, 15, 6, 8. Suppose the requirement of the 3 different processes are P1 is 15, P2 is 6, and P3 is 8. And for every user in one cycle, 20 milliseconds of CPU is allocated. Then if you execute in the order P1, P2, P3 mean you can complete only P1 because you can't complete even P2 because P2 requires another 6 seconds. Instead of that one, if you execute in the order P2, P3, then P1 mean, then you can complete two execution. You can complete two process execution. So in that case, in the first case, we execute in the order P1, P2, P3. Since you can complete only P1, your throughput is only 1. The second example, suppose if you execute P2 first, followed by P3, then finally if you go to P1, then within the same 20 milliseconds, now we can completely execute two different processes. So the second case, the CPU, the throughput is 2. So higher the CPU utilization, higher the throughput, better is your algorithm. The third one is turnaround time. Turnaround time is the total time difference between time of submission till the time of completion. The entire duration, the difference we call it as turnaround time. Turnaround time includes so many things. It includes the period a process spent waiting to get into the memory first. After getting to the memory, it may not get the CPU immediately. It has to wait till the CPU is free. Second time. Then that means it has to wait in the ready queue for some time. Then after that, it will get the CPU. It will execute for some duration. After that, it needs some IO operation. Then from the running state, it goes to waiting state. It has to wait for a particular device. After it gets the particular device, it gets serviced by the IO device. Once again, it comes back to the ready queue. Stay there for some more time. Once again, it is picked up by the CPU. So all this time we add together, the total time duration, we call it as turnaround time. So the next one is waiting time. How much time the process has to wait in the ready queue to get the CPU. The time we call it as waiting time. And the next one is response time. So you submit a job at a particular time, and after some time you will get some response from the system. Then that difference time of submission to time of first response, that time duration, we call it a response time. So far we have considered 5 major criteria regarding CPU scheduling. One is CPU utilization, second one is throughput, turnaround time, response time, and waiting time. Out of these 5 criteria, always you should have higher CPU utilization, higher throughput, but less turnaround time, less waiting time, and less response time. The last 3 should be minimum. The first 2 should be maximum. Such an algorithm is considered as the best algorithm. So all this, the selection of algorithm depends on these 5 criteria. So some of the review questions to check your level of understanding. These are some of the questions that may appear in your examination. What is CPU scheduling? CPU scheduling is an algorithm that decide which process in the ready queue should be serviced first, which process in the ready queue should be serviced next, etc. Distinguish between preemptive and non-preemptive algorithm. I have given so many difference between them. Discuss the various CPU scheduling criteria. It could be. So the some of the CPU scheduling criteria are throughput, utilization, waiting time, response time, etc. So I framed some important or some interesting multiple choice questions on today's class. Which of the following is a non-preemptive scheduling policy? Shortage job, round robin, first come first serve, and both ENC. So shortage job first and first come first serve are the examples of non-preemptive, whereas round robin is an example for non-preemptive. The correct answer is both A and C. Selection of process in the ready queue for CPU allocation is done by, if there are several processes in the ready queue, only one will get the CPU at a time. Which process will get the CPU? That is decided by short-term scheduler. So the correct answer is C. For optimal performance, which of the following should be minimum? Generally, we want CPU utilization to be maximum. Response time should be minimum. Average waiting time also should be minimum. So the correct answer is B and C. So the correct answer is D. If scheduling takes place when the process is moved from running state to ready state, this happens during interruption. High priority job tries to interrupt low priority job. It is said to be preemptive. The correct answer is A. The last question is average waiting time depends on how many processes are there in the ready queue. CPU burst time of each process, only A, both A and B. It also depends on number of process as well as the requirement, CPU burst time requirement of every process. The correct answer is both A and B. Students, in today's class, we learned 3 major concepts. One is the criteria for selection of CPU scheduling. Categories of CPU scheduling policies, preemptive and non-preemptive. The characteristics of both preemptive and non-preemptive. Advantages and disadvantages of each of these two. Hope you understood the topic that I have covered in today's class. Still, if you have any doubt, you can contact me over that number, or you can post your query in the comment section of the Google class. Okay, with this, I will conclude today's class. Okay, have a nice day.